What we'll do now is we will work an example problem involving a Rankine cycle that's a little more complex than the one that we just took a look at. So this is a second example. And for this one, what we're doing is we're looking at a reheat regenerative Rankine. So I'll begin by writing out the problem statement, and then we'll proceed through the solution for this problem. So there's the example problem that we have before us, and as with all the examples and all the problems, the first thing to do is to extract out the pertinent information that we will need to solve this. And so one of the pieces of information, we're dealing with an ideal reheat regenerative Rankine cycle. And so that gives us an idea in terms of how this system is constructed and designed. We're also told the net power output. So the total output of the plant is 120 megawatts. Other pieces of information that we're provided with is the conditions going into the high pressure turbine, 10 MPa, 550 degrees C, and the steam is then leaving the high pressure at 0.8 MPa. That's when it would then go back into the low pressure turbine after going through a reheat. Now, when the steam is stripped off the high pressure turbine there at the 0.8 MPa, some of it is used to heat the feed water. So that is boiler feed water. And we're told that it is being heated in an open feed water heater. And so we've discussed two different types of feed water heaters, closed and open. This is one of the types, and so that tells us a little bit about the design of it. Other information that we're provided with here, we go through a reheat process back up to 500 degrees C. That would be at the 0.8 MPa. And then we go through a low pressure turbine and we go all the way down to the condenser pressure of 10 kPa. So the things that they're asking us to look for in solution of this problem, the first thing they're saying is find the solution or write it out on a TS diagram with respect to saturation lines, which is always good practice. We should do that anyways. The next thing they tell us, find the mass flow rate of steam through the boiler. And then the last one is the thermal efficiency of this cycle. And so that's the example problem that we have before us. What we'll do is we'll begin by writing out some of the pertinent information there, and then we'll begin by doing the process diagram as well as the process schematic. So let's get started on doing that. So to summarize, we have a reheat regen Rankine. We're told that it has 120 megawatts as the total power coming out. Other things that we're told, high pressure turbine, has steam coming in at 10 MPa and 550 degrees C, and the low pressure turbine, we were told that it operates at 0.8 megapascals, and the steam coming in, oops, there's a mistake there, I apologize. That should be 550 degrees C is the temperature going into the high pressure turbine. And then in the low pressure, we're told that the steam comes in at 500 degrees Celsius. That would be after a reheat process. And finally, the condenser, the pressure that we've been provided with is 10 kPa. And the things that we're looking for, A is m dot boiler, or the mass flow rate through the boiler, and B is the thermal efficiency of this cycle. So the first thing that we're going to do, we're going to write out the process schematic and the process diagram, and then we'll work on getting enthalpy at the different states within the cycle. So what we have here is our process schematic as well as the process diagram. And what we need to do is we need to map the state information between these two diagrams. So we'll go about and do that now. So there we have the state correspondence between the process diagram and the process schematic. And you notice states 6 and 7 are coincident because those are both the exits off the high pressure turbine, and one of them is being stripped off and sent through the boiler for a reheat, and the other one is used as part of the regeneration process. Now, what I'm going to do is draw arrows onto our diagram to show the direction of the fluid flow. And so here we have fluid flow in that direction, and I go back up and then come back down through the condenser. Now the other thing that I need to do, I need to assign the mass fractions because we're stripping some of the mass out and not all of it is going through our system. So the place when we come out of the high pressure turbine, we have 100% mass flow rate there, but then we split into two streams. And so one of those I will denote by 1 minus y, and the other one I will denote by y. So y% is going into the open feed water heater. And the way that we define y is mass flow rate 7 divided by mass flow rate 5, which m.5 is the mass flow rate through the boiler, m.7 is the amount that we strip off and send through the open feed water heater. And so I will continue with that convention on our diagram. And then with that, 1 minus y goes through the boiler for regen, goes into the low pressure. So we can say what is going through the condenser is 1 minus y. And then when it recombines back, we're back at 100% flow rate going into pump 2. And then putting the same sort of information on our process diagram, we would have 1 minus y here, and then the bleed system or stream that is going off and going into the open feed water heater would be y%. So that is the process diagram and the process schematic. The next thing that we will do is we will go ahead and we will start to get the state information. Once we have state information, we can get enthalpy, entropy, things like that. And after that, we will then look through and start doing the first law analysis.